Hello everyone, we're going to take a look at the Persist Connect IoT device that we built. I'm going to share my screen to show you guys. So to start with, um, we have the code here which we used. Essentially, we have used an IoT device board which is powered by ESP32, uses TCM 7000 module to connect to the internet in general, and we also have Wi-Fi capability and also Bluetooth capability on the board. To go through the code, essentially we're using our basic libraries, and then we are currently connecting through Wi-Fi. And essentially we are connecting to an MQTT server, which is going to be Amazon AWS. Along with that, we're also going to redundantly connect to another third-party server. The device is going to send messages to both the systems essentially, and so there is security in place for both of them. To start with, we have the username password required for third party broker, and we have the certifications required to log into AWS as well. This is the root certificate, and this is the root certificate for Hive MQ, the third party broker. And then we have the device certificate that the device needs to be able to get onto AWS. And we also have our own private key without which AWS cannot be accessed. After that, essentially, we have some functions that we have declared, which is trying to connect to the clients, essentially AWS and HiveMQ. It connects to both of them. And then it also measures, it has a counter which measures the number of messages that it is sending, essentially. And it's also trying to initialize the time, and it connects to Wi-Fi. And then it has a callback function which essentially there are two topics, essentially two channels through which one channel is ideally only for the IoT device to send data to AWS and Hive MQ broker, and the second channel is for two channel communication where we can send alerts and notifications without any disruption to the data being sent in terms of the sensor data being sent. And in the second channel, which is topic B, we'll be sending alerts as well as receiving communications, which can be used to switch on or switch off two buttons or two switches on the IoT device, which can be used to power turn off the entire system on the vehicle or turn off charging essentially. And essentially we here connect to the MQTT brokers. These are the functions used for that. And then this is the function where all of the sensor data is encoded into a CAN bus protocol. This is very necessary as this enables two things. The first thing is that the IoT device can actually communicate to other IoT devices or other vehicle components that are typically in the automobile industry and have the CAN bus protocol. And if any board such as the BMS or other systems are giving us CAN information, it can be decoded using the same program. So this enables us to collect the data and send all of the data in a CAN system, which means that this can be integrated into other automobiles as well and other automobile systems also, because all of them are CAN enabled. And this is the function that is essentially collecting data from two temperature pins, temperature pin 1, temperature pin 2, and then it is also taking in the current value and the voltage value. It's calculating it and calibrate. This is calibrated. And then it's also taking all of them and putting them into a message, which essentially is in a JSON format, which will be sent to the through message to the broker. And in terms of setup, it's a setup where all of the functions are set up in terms of connection to the brokers, essentially. On top of that, we have in the loop, we have the consistent, we have the functions being called or the consistent connection, ensuring that always it's connected. Every message that is published is being checked. And if it is not being published to the server, software tries to reconnect to the system, essentially. And here we have what we're trying to publish to the broker at the end of the day, and this loop keeps running. Now let me connect uh, so this is the device that we're working with essentially. This is the baseboard. This is the baseboard that has a GPS antenna, an LTE antenna. It can also be powered through an 18650 cell, and it has a SIM card on it, and it has the ESP32 control chip on it, which we are essentially using to as the brains of all of our operations. And this single board can power all of those systems. It can perform a lot of edge computing and on-device calculations as well. So I'm just trying to connect it to the system right now to be able to show how the serial monitor port looks. So essentially here you can see that it's trying to connect to the Wi-Fi. It's connected to MQTT. It's connected to MQTT AWS broker as well as Hive MQ broker. And then it does some processing. It's trying to collect the data, and then it's trying to send a message. And as you can see, the message has been published to the broker. This is the first message. It's programmed to send a message once every 20 seconds. And also on the topic B, an alert is being sent, saying alert, your vehicle is too hot. This is just uh, a placeholder alert which can be sent, which can be triggered based on some rules on device itself. So here in the message, as you can see, we will also check it out in detail later on, but essentially it has the device ID, the timestamp, which you can see it fetched online, and the number of reconnects it had to do. And then the messages sent since reconnect, and also the sensor data essentially in a separate packet that can be queried. Temperature one, temperature two, current, voltage, and CAN bus message. So this is the entire sensor data which has been encoded into a CAN bus system. And essentially, we also put a system in place to prevent recursive messaging on topic B, because topic B is a channel where conversation is happening both ways. So the IoT device has to recognize when it's sending a message, it should not trigger back a response, right? So there is no response for the alert your vehicle is too hot message. Um, as you can see, it's keeping publishing every 20 seconds, and the alert your vehicle too hot is set to publish every 30 seconds. So this is what is happening on board um, currently. So now uh, I will disconnect the system from the USB. And as you can see, it's been disconnected and it's on its own. Let's go to the broker now. So if you go to the broker, I'm going to start you can see that the messages that we saw there are being displayed here on topic B and also on topic A. Topic A is essentially for the sensor data, and topic B is for the alerts, and it can also receive messages. And this is AWS IoT Core, and there's a redundant broker, which is a whole different broker. It's sending messages to both systems. So you can see the messages are being received here as well, in Hive MQ as well. So now I'll do something. I will clear all these messages. Um, and I'll also clear all the messages in AWS, so that we can show a demonstration of how it works when we are this is essentially not connected to any system right now. It's on its own. It's being powered by this battery. So there's a turn on system which I'm going to turn on. If I turn on, the blue light is going to blink and it's going to do its process, and we will see message here automatically in topic A in a couple of seconds. So it's taking the time to connect to Wi-Fi. This is happening only once. So as you can see, we have the first message. It has not yet retrieved the time, so that's why you can see 1978. But it takes a couple of minutes, but it catches them. This happens when it gets reset or when it gets switched on for the first time. As you can see, these are the values that it's not currently connected to any sensors, but all the pins are configured. So it's giving the base values essentially at this point. So there's a temperature one, temperature two, current voltage, and all of this data together in a CAN bus format. The CAN bus we have a protocol which is also presented in the architecture document, which you can be checked out. So you can see messages are being published every 20 seconds. This is topic A, and topic B, essentially Persist Connect is saying that alert, your vehicle is too hot. Right, so there's a third message here, and the same thing happens with web client as well, where you can see we are raising messages every 20 seconds on topic A, and then the persist con alert is on topic B. So now topic B also has an interesting thing. So if I there's a message that we have put which is switch one on and switch one off. So essentially, I'm going to publish this message through this broker to topic B, and when I do that, the system is going to recognize this, and as you can see, here it is. I said switch one, I sent a message switch one on, and the system has switched the switch on and it has replied back persist confirmation switch one turned on. Now all of this is happening independently on the system, on the board itself. There is nothing in between. It's all happening. The communication is happening over the internet. There is no physical connection. It gets a signal, then it's switching on the pins. It's changing the status of the pins, GPIO pins essentially, and you can see that it's confirming it's turned on. Now let us try switch turn off as well. So if we publish this message, essentially, as you can see, there's confirmation that it has been turned off. This message is being sent by the IoT device. After reading this message, it reads this message, send this confirmation, and also prevents non-recursive uh, messaging, where it knows that it sent the message, so it won't read again. So let's send a unrecognized message right now. And it says error unknown command. So it knows what are the commands that it needs. Essentially, this format is necessary because this is what is going to be sent to any API when an API wants to fetch it out. This is going to be necessary. It's in a JSON format. It can be further developed into a database. Essentially, this is how the communication system is happening. Now, I'll stop sharing this, and we can also check out on the phone. I'll share the mobile screen, and you can see it's a mobile client essentially. So we can see the message that are being sent on message also. So I'll go ahead and clear the past messages so we get the fresh messages. There it is. On topic B, it is persist con alert, and sorry, and topic A is the JSON format. So this is happening on the mobile as well. And so all of this is happening on the chip itself. There is no external processing happening. And on top of that, I'm also going to show. So this is the box in which the device is going to be housed. It's a 3D printed box currently, but it's a very small box, and it houses the whole system. It has a system inside it, along with in the behind there is the antenna as well as the GPS modem. So it's a very small box. It's entirely encloses the whole system, and it also has space for the reset button and the boot button. And it has access. It will be a button here, which essentially ensures that we can switch on and switch off the system, and this connection to the USB-C. It has space enough to hold for the 18650 battery as well. And this is the test prototype box that we have designed for this. Thank you. I also wanted to share how we set up the entire system. So this is AWS IoT core, where in the things we have a certain thing for us that we have defined. It has its own ARN, and it has its own certificate type, and we have defined the certificate type uh, by creating the persist con policy, which is a policy essentially which allows it to connect, publish, subscribe, and receive messages. Essentially, this is the policy that has been defined, which allowed us to download the certificates that we used in the code. This is called persist-con policy, and essentially this is the things that we have, which is persist-con. It's a type of a thing, and we can create multiple of this essentially. And in the test client, uh, essentially this is the test client, and here we have to do topic subscription essentially, which is what happens on the back end. Um, and the messages are currently being sent to both these channels. Now we can take both of these channels and we further connect it to Lambda, which connects this data, takes this data even while the system is not working, and we can have it stored into a S3 instance, which is what the next step is going to be for us. On top of that, we also have the web client, which is HIVE MQ. Essentially, AWS is a more rigid system which could probably be used for heavier processing for the company purpose and for data collection purpose and for safety standard purpose on the back end for the company purpose. And the web client, which is HiveMQ, could be an additional redundant system which can typically be easier to deploy on mobile systems. Essentially, that is the idea here. We might eventually end up going with either or, but currently we have a redundant system where each message is going to both AWS IoT as well as Hive MQ web cloud. We also are designing a interface for this where it's a screen with a screen which can interact with all of this data on without being connected to internet as well. But this essentially this message is going to be very necessary to be able to understand vehicle performance, and this actually can send GPS data also, which is currently not being sent currently because it needs to be in the open sky currently to be able to connect to the GPS system, so that's not being seen there. So it can work on GSM, it shows GPS data, and it's working perfectly fine with very good, with no problem in terms of connection and no latency. The service is really good, and all of this data is in JSON format can be directly sent to a mobile API. So this is a very good, very minimalistic and very EV focused system that we've been able to build currently.
Connected, sir.
Switch it on.
Connected, sir.
Switch it off. Switch it on. Switch it off. Switch it on. Switch it off after 5 seconds. How much current did we use?